Right, so good morning everybody and welcome to the Center for Theoretical and Computational Physics weekly seminar. And today it is a pleasure to have with us Daniel Bonn from the University of Amsterdam, where he is a professor of physics. Daniel has worked on many different topics in soft matter physics and related areas, namely wetting, as well as more exotic topics such as quicksand and more recently the possible spread of coronavirus through droplets. But today he's here to talk to us about something a little different, something that's, well, perhaps very popular in the Netherlands, but a bit less so now, which is ice skating. So over to Daniel on the physics of ice skating. Before I actually hand over to him, this seminar will be recorded and made available on our YouTube channel. So by staying on, you're giving permission for your voice and image to be recorded. In the interests of internet stability, I ask everybody to keep their microphones muted and their cameras switched off during the seminar, except the speaker, of course. However, if you do wish to ask a question, you're quite free to unmute yourselves, and if you like, switch on your camera as well. So it's over to Daniel now. Thank you.
Thank you, Polo, and thanks for the invitation to speak. I was actually thinking you were contacting me to speak about the coronavirus, because I do that a lot these days, because I didn't know that the Portuguese were actually interested in skating. The Dutch are, and so I want to start off with a video that was filmed the weekend before last on the canals in Amsterdam. So I'll go to my presentation, my serious presentation now. But this was just 10 days ago, and so the whole of Holland is still completely mad about ice skating because we skated on the canals for the first time in, I think, 12 years. And so what I want to discuss with you today is the question, why can one actually skate on ice? So I have this lovely classical Dutch skating painting from Hendrik Averkamp, who only painted scenes like this. And so the Dutch have been skating for a very long time. And the Dutch are also very interested in why one can skate. But as I will tell you, there's actually some new insights into the reasons why this is possible at all. And so this research, as I will explain later, started out as a fight between me and my brother Misha, who's at the Max Planck Institute for Polymer Research. And my brother is a spectroscopist who's very interested in water and ice and who saw something that was very interesting, but that I didn't believe. And so in the end, there's almost a whole soccer team that worked on this, but the main players here are Bart Weber, my former PhD student, Rinse Lievering, my current PhD student, and also very important is Yuki Nagata, simulation guy from the Max Planck Institute. So let's first ask the question, why would one be interested in friction anyways? And so I have a lot of students working on friction because it's such an important topic. Depending on who you ask, it represents between 10 and 30% of the world energy consumption. Depending also on whether you count wear as part of friction, if you have to replace a worn part. that is due to friction, of course, and the fabrication of that worn part can also be counted in the part of friction in the world energy consumption. The Egyptians were among the first people studying and actually using friction. This is a beautiful tomb drawing of the tomb of Jehuti-Hotep, showing how a 60-ton statue was dragged through the desert by a large number of people. And the interesting friction aspect is that there's a guy standing in front of the sledge, pouring water onto the sand in front of it. And if you want to know more of that, we wrote an article about this a couple of years ago that I still find very amusing because among many other things, we published this tomb drawing in PRL 5,000 years after it was originally made. So friction is very important. And if you can understand friction, you might be able to do lots of interesting things. And so I don't know if you've ever seen a dog amazed, but this dog is really very amazed by the ice on the road, showing how slippery ice actually is. And so if you think about friction and wear, it would be lovely if you can understand this to potentially use it in all kinds of applications, because the friction of ice is typically a factor of 5 to 10 lower than any other on any other material. And so for the Dutch, it's of course very important that you can skate on ice, because the Dutch, as we'll explain a little bit later, are the best ice skaters in the world. Another interesting engineering application of friction is the building of the Forbidden City. It was actually discovered fairly recently how they transported all those huge stones. They're stones that weigh 200 tons, and they actually waited until winter, poured water on the roads, and then slid the large blocks over the ice road. Yeah, and so that is how a large part of the Forbidden City was actually constructed. If you think about the building of the pyramids by the Egyptians or the building of the Forbidden City by the Chinese, it's really amazing that they could transport such huge loads without any machines. Yeah, and so that's another interesting application of ice friction. Now, if I ask any of you what friction is, why ice is so slippery, I'll probably get either of three answers. There's still people who believe that because the liquidus or the liquid solid phase transition in the pressure temperature diagram has the wrong slope, it actually means that you can melt ice by exerting pressure on it. And so if your skate exerts a large enough pressure, it will in fact melt the ice. There's two problems with that. The one is that the pressure exerted by a skate is actually not high enough to melt ice. And the second, and perhaps even more important problem, is that below minus 22 degrees C, the phase diagram of liquid water and ice actually tells you that you can no longer melt the ice. And the Dutch know that if we cannot skate our famous 11 city tours in the Netherlands, we skate it in Norway or Sweden, and there the temperatures are often close to minus 30 and still skating is possible. Yeah, so the pressure melting is a widespread belief, but if you think about it, it's actually not the correct explanation for why one can skate on ice. The other idea that is widespread is that some solids melt at their surface before they do so in the bulk. And so if ice does the same thing, you could have a water-like layer at the surface of ice that could lubricate your skate if you're close enough to the melting temperature. That's called pre-melting. But again, this layer is if present at all, not very thick, and only present very close to the melting point. And so it's also, this explanation is not really a very convincing explanation for why one can skate on ice. The most accepted probably explanation is that the skating itself heats up the ice because of friction generating heat, and this frictional melting then creates the water layer that allows you to skate on the ice. But if you look carefully at this movie, this little child actually doesn't go very fast, and by the time she, I think it's a she, falls, she's actually standing still. Yeah, and so frictional melting is perhaps important for high-speed ice skating, but for explaining the slipperiness of ice, I don't think it's the correct explanation. Yeah, because it can't explain low velocity skating. And so of the three common explanations of ice skating, I actually don't believe either. And so we have to think about ice skating perhaps in a different way. By the way, if you have any questions, or if I go too fast, feel free to interrupt me and ask me any questions. So the three explanations are not completely convincing. Fortunately, there was a very clever experiment by my French colleagues, headed by Liedrich Bouquet, published 1.5 years ago in PhysRevX. And they had a very nice experiment where they have what they call a tuning fork with a bead attached to it, and the bead slides over ice. And what you measure is the change in eigenfrequency of the tuning fork when the bead touches the ice. And it turns out that the change in frequency has a real and an imaginary part, suggesting that the ice is actually viscoelastic, which complicates things even more. And so their explanation of the ice skating is that ice is slippery due to the fact that the outermost layer of the ice is actually not water, not ice, but sort of a slush puppy, this lemonade, this frozen lemonade that I think is pretty common in Portugal also, with little ice crystals floating around in water. And so they claim that this is the correct explanation for the slipperiness of ice. And so this is about the time that we also got involved in ice friction measurements. And so basically all you need to know about friction to understand this talk was already discovered by Da Vinci. He did a lot of sliding experiments with, for instance, different wooden blocks on wood. And so his two most important findings were that the friction force doesn't really matter on the contact area. So this is a block sliding over a piece of wood, but if you would put the block on its side, the apparent contact area would be much smaller, but the friction force would be the same. And the second important thing that Da Vinci found is that whatever you measure as a friction force is always proportional to the weight of that object. So if you make the object twice as large, you need twice as large a force. And so his conclusion was that the normal force, which is the weight of the object, and the friction force have a constant ratio. And then he added something very interesting. He said this ratio is universal and should be 1/4. And we know now that is not completely true. It's always of this order of magnitude. But the friction coefficient of steel on steel is clearly different from the friction coefficient of rubber on steel, for instance. But still the proportionality of the normal and the friction force has remained intact. Okay, so let's do an ice skating experiment in a laboratory that looks like this. This is a Rheometer tool, so we abuse a Rheometer to do our friction experiments, and our friction experiment consists of having a little metallic ball, which is our model skate, if you like, that we slide over an ice surface in between temperatures of -100 degrees and 0 degrees. And that is important because the large temperature range actually allows us to say many interesting things about the friction. The Rheometer is an excellent instrument to do such friction experiments because it measures the torque necessary to rotate the tool, which we can convert into a friction force F, and we can push harder or less hard on the ball onto the ice surface and measure the resulting normal force. And as I explained to you, Da Vinci already found that the ratio between those two forces is constant, and that ratio we call the friction coefficient. And so the friction coefficient, as also Leonardo explained, is a property of the two materials and doesn't depend on the shape, the size, or the roughness of the materials. In principle, at least that's how engineers think about it, and we'll see where we get with the friction on ice. So we plot this friction coefficient as a function of temperature, and then we get our first surprise, namely that the ice friction is completely non-monotonic and does all kinds of interesting things. So if I'm at -100 degrees C, we're actually a little bit below even, we get a friction coefficient of roughly 1/2. And that is a friction coefficient that is typical of your foot sole on the pavement, meaning that you cannot slide at all. Then if you increase the temperature, you go to lower and lower friction coefficient. And then right around here, you go below 0.1, and below 0.1 is really very slippery. So this is the range where ice is slippery. But then if you go too close to melting, it actually goes up again. And so this is really already a very interesting finding that we need to try and completely understand before we can say anything sensible about the mechanism of the slipperiness of ice. Now, let's first discuss the easy part. Why is it that the friction coefficient goes up close to melting? And this is something that you might have actually experienced yourself. If the ice is too warm, if you go ice skating, it actually becomes hard. In any case, any Dutch child knows that. The first experiment we did to try and see what happens is we measured as a function of the speed of the sphere sliding over the surface. And we basically find over more than 4 orders of magnitude that the friction coefficient is very low. It's here something like 0.01, very, very, very slippery, but doesn't really depend on speed. Yeah, and this is again an argument against frictional melting. because if you go very fast, you would expect a large amount of frictional melting, and if you go very slow, no frictional melting. And so if the frictional melting is important, you would expect the friction coefficient to depend on speed, which it doesn't. What does give a clue about the mechanism is if we look at the Da Vinci plot, if you like. This is the friction force and this is the normal force, and so Da Vinci said that they should be proportional, and they sometimes are, but mostly not. And notably, if you go to temperatures very close to the melting point, you get a dependence that is close to 3/2, which I will explain to you in a second. But what is more striking is that you see that the ball, if you go close to melting, actually leaves a circular trace in the ice. So basically, you're no longer skating on the ice, you are plowing through the ice, and that's where the 3/2 comes from. If you go to very high temperature, you actually get the result for Hertz contact, because you have a sphere on a flat plane, and for a sphere on a flat plane, you would expect this 2/3 power. So low temperature, no trace, and bona fide skating. High temperature, you leave a trace, and so you're no longer skating, you're actually plowing. So you go from elastic to plastic, if you like. And so plowing friction is something we can actually understand quantitatively. So the plowing force is the area created by the sphere in the plowing through the ice. So it's really the plowing area times something called the penetration hardness, which is the plastic modulus of the ice. And so if you know now how deep the sphere goes into the ice, then you can calculate the plowing force. And if you know the penetration hardness, you actually do know how deep the sphere goes into the ice. And so if you do that, and you can immediately calculate the plowing force and retrieve, if you like, the 3/2 power that we found in the experiment. Now we measure the penetration hardness of the ice. The penetration hardness measurement is a very simple measurement. You take a sphere or you take a cone, then you try and push it into the ice. You measure the force and the penetration depth, and from the two, you can directly get the penetration hardness. And so, as you might have guessed, the penetration hardness is very high at very low temperatures, but steadily decreases when you go towards the melting point. And so what happens is that if you are at -60, the sphere simply slides over the ice because it has not a large enough force to plow through the ice. At -20, you start plowing, and at -5, you really leave a considerable trace on the ice, in the ice, I should actually say. And so that is what we also saw in the experiment. And you can now make that quantitative with the calculation and the measurements, and then you get the blue curve, which quantitatively describes the behavior very close to melting. So far, so good. Dutch children know this. You shouldn't go and skate on the ice when it's too warm, because it becomes really very difficult and you leave all these traces. The interesting question is now what happens here. And so this is where I got into a fight with my brother, because my brother is a spectroscopist and he looked at the surface of ice and he saw or interpreted his spectroscopy data, in any case, in such a way that they found that the first bilayer of ice melts at something like -70, this arrow here, and at something like -20, the second bilayer melts. And so here you get the first thin water layer, and here the water layer becomes thicker. And so this is why I did the experiment originally, because I was thinking, well, if the low friction of ice is due to a water layer, and this water layer forms discontinuously, this should show up right away in a friction measurement. And so the friction measurement is still the same friction coefficient as a function of temperature, and it goes down and nothing interesting happens at -70 or at -20. What is interesting is the very steep temperature dependence of the friction coefficient. As I said, at -100, you can easily walk over the ice without slipping, whereas at -20, it's impossible to remain afoot. And we can fit this behavior actually to an Arrhenius law. So the friction coefficient seems to depend on temperature by the exponential of some activation energy over kT. And the question is then, what is that activated process? And so we went back to the question why people think there's a layer of water on the ice. And that's basically due to Faraday, who took 2 ice cubes outside on a cold day, put them together, and then they sintered together. Yeah, you couldn't detach them anymore, one from the other. And so Faraday's reasoning was that since the water molecules have to come into the register of the crystalline lattice, they must be mobile, and therefore there must be a water layer. However, as many people have forgotten, this experiment was later done quantitatively by Professor Kingery from MIT, who was a ceramics professor actually, and so the ceramics people are very interested in sintering. And so he did this with 2 ice spheres and looked at how the neck between the 2 spheres actually grew. And so here you get the neck radius as a function of time, and you see that instead of going linearly as one would expect if there would be a layer of liquid water, the slope is actually much, much smaller. It's actually a slope of 1/7 is what Kingery found for the radius as a function of time on a log-log scale. And so Kingery concluded that this 1/7 law was characteristic of surface diffusion in this particular geometry. And so he said that the welding together of the ice particles is due to surface diffusion, which gives the 1/7 law, and which is very rapid. So here you see the radius growing over a period from 1 to 10 minutes. Yeah, so this is a fast and thermally activated process with an activation energy just a few kT, and that's actually exactly what we found for the friction coefficient. Yeah, and so the question that we asked ourselves is, would it be possible that it's just the mobility of the ice molecules of the outermost layer on the ice that acts as sort of a molecular ball bearing and slide or rotate very easily so that it would sort of lubricate your skate. And so this is where the simulations of Yuki Nagata come in very handy. So this is the crystalline lattice, and you see he visualized only one water molecule, which is this thing here. And so it turns out that there's different types of water molecules at the ice surface. There's water molecules that have 2, and there's water molecules that have 3 hydrogen bonds. And these molecules that have 2 hydrogen bonds are so mobile that you can see them moving over the surface in even less than a picosecond. Yeah, and so that means that it's sort of a 2D gas, if you like, of molecules that are still within the crystalline lattice, but that are so mobile that they can change places very easily. And so it turns out that the reciprocal of the diffusion coefficient, which Yuki gets from his simulation, has exactly the same temperature dependence as the friction coefficient, showing that the interpretation of these rolling molecules that lubricate your skate is actually not so very stupid. Yeah, and so this is the friction coefficient in black, the diffusion coefficient in red, and so that actually accounts for all the low temperature behavior in quite a satisfactory way. If that is true, if the mobility of these molecules actually does lubricate your skate, that would also mean that if these molecules become very slow, that skating should become very difficult again. And there you could also expect speed dependence if the rolling of the molecules is not sufficiently fast at low temperatures. Your friction should go up with increasing speed simply because those rolling molecules cannot keep up. And that is exactly what we find. So at -7 and -21, we have this low and constant friction coefficient, whereas at -90, actually, the rolling molecules cannot keep up with the moving sphere, and therefore you get an increase in friction coefficient with increasing friction, with increasing velocity, sorry. There's another interesting experiment shown here for the believers in the water layer. What one can do is one can take plastic surface, high density polypropylene that has the same mechanical properties as ice, and one can do a dry sliding experiment and a sliding experiment lubricated with water, and you see that they actually give high friction coefficients, and that the addition of water only matters at really high velocity. So the water layer actually doesn't explain at all why skating is possible. And you already knew that, of course, because if I would pour some water on your kitchen floor, which also could have the similar properties as ice, if I pour some water there, it's impossible for you to skate on that. Yeah, and so the conclusion is that ice is not slippery because of a water layer, but rather because of the existence of a mobile surface layer of ice molecules. And I stress that these are ice molecules and not water molecules, because the simulations clearly show that they are within that their position is always within the crystalline lattice, even though they are very mobile. Perhaps the most interesting finding is that if you measure the friction over a large temperature domain, you get a minimum somewhere right around -7. That is the optimum skating temperature. And if you ask the ice master of the great skating rink in Holland, Tielf, what the fastest ice temperature is, he says he always keeps the ice at -7 because that's where the lowest skating times at different distances are reached. Yeah, and so we The ice master already knew that, but now we actually understand why that happens. Okay, now if you're Dutch, you can't come away with just dragging a ball over a surface. You have to actually do a real ice skate. And so this is our real ice skating experiment. This is actually a piece that we got out of a real skate, and the part here that touches has the right radius of curvature that comes from the skate, and that is important. Yeah, and this is part of the PhD of Rinse, who will defend his thesis shortly. Okay, so why do we care? Well, so basically skating is the only sport in which the Netherlands is really the best in the world. This is a statistic of the medals won over the past 10 years, I think, in international championships, and the Netherlands are clearly leading. And so one of the questions I got asked lots of times from journalists is whether we can actually use any of this knowledge to improve the skates. So let's ask the question what the best ice skate is. And so part of it is, of course, the geometry, and we had this curve that was for our little steel ball. Now, let's approximate the skate as a spherical cow, if you like. If you take a much larger sphere, you immediately see that the result becomes very different because the sphere is larger, the normal force gets distributed over a larger area. And so the increase due to plowing friction happens at a much later time. Yeah, at a much higher temperature. And so the ideal skate, this is what I just said, the ideal skate is, of course, the real skate, because if you ask the people making the skates, they say actually that the radius of curvature of such a skate is something like 10 meters. And so they have very precise machines that allow to make such a very large radius of curvature over such a relatively small distance. And so if you do, you can actually see, if you look very precisely, that the plowing is actually even less for the real skate than for the spheres. Yeah, and so this was very informative, but it doesn't allow us to improve the skate of the skaters because they already knew this. The other thing that one could worry about is the roughness of the skate. Should it be rough? Should it be very smooth? You could argue that if your skate is rough, that there's only a small contact area between your skate and the ice. And so the smaller the contact area, perhaps the smaller the friction coefficient, because you have to displace less of these molecules. And so we can do different roughnesses. This is again a sphere. We can make the spheres rough, and we see, as you would intuitively expect, that the smoother the skate, the lower the friction force. And that's very interesting. So we tried to quantify this. We use optical profilometry to actually determine the roughness. We subtract the curvature of the sphere, and then we get some roughness profile that we can characterize by its root mean square. And then we can see that we can see two things. One, the Arrhenius behavior actually disappears or becomes attenuated, if you like. And the second is that at close to melting, it actually is very difficult to skate if you have a rough skate. And so the fact that it's difficult close to melting is easy to understand. If you have a rougher skate, you will actually plow more, and the plowing is difficult. And so this is a profilometry image of the ice after a rough skate has passed. And you see that you leave really very deep traces into the ice. The non-Arrhenius behavior is perhaps even more interesting. So what we do is we take the roughness of the different sliders and we then do a contact calculation using a finite element package that is readily available. And so if you, from such a package, you get the area of real contact between your sphere and the ice, supposing that the ice is actually smooth. And if you know the normal force and you know the contact area, you actually know the contact pressure. And it turns out that the contact pressure is very important in what happens, because if you look at the normalized shear stress, so this is the basically the friction force normalized by its Arrhenius behavior as a function of the contact pressure, you actually see that the shear stress goes up relatively steeply if you increase the contact pressure. So if you basically touch the ice only with a couple of points of the roughness, it becomes very difficult to skate, and that's not because of the plowing, but it's because you push out this layer of very mobile molecules if your pressure is too high. Yeah, and so this line is actually the theory that predicts the pushing out of the layer of mobile molecules, and the data is data from different temperatures, different pressures, or different normal forces and different roughnesses. Yeah, and so this is once again a proof that it's not just the water layer, it's really the layer of mobile surface molecules. And if your skate is too rough, you will push them out and it becomes impossible to skate. Okay, I'm at the end. So if I have to conclude something, that I would say that ice is sometimes slippery. At very low temperatures, it's impossible to skate, and if your skates are too rough, it's also impossible to skate. But the two dominant mechanisms are plowing through the ice close to the melting point. We understand that quantitatively. Surface diffusion far from the melting point. We understand that semi-quantitatively. It's still not possible to relate the diffusion coefficient of these mobile molecules to the friction coefficient directly, but the correlation is clearly there. The best ice skate is, of course, an ice skate with a very large curvature and a very smooth surface. Unfortunately, I cannot help the Dutch get more gold medals because we knew all of this a long time ago. And so I think we've understood a little bit better what ice skating is all about. What's next is, if you think about the surface diffusion mechanism, that also means that if you would make a scratch in the ice, that it would spontaneously close up by the surface diffusion of these very mobile molecules. And so we tried that in the lab again with the profilometer. And here you saw a scratch that disappears. These are simply grain boundaries in the ice. I'll show it to you again. Yeah, so we make a scratch with a needle basically, and then you just over a time span of a few minutes, you see that disappear. And this is the height profile of the scratch, and you can see also that it's the same scratch disappear over time, so you can quantify what happens here, and again relate that to the diffusion, the surface diffusion coefficient of Kingery. So the ice part is really very interesting. What I want to end up with is what you would really want to do is, of course, to have ice-like very slippery surfaces at room temperature. And there's one way in which this can be done, and we're actually investigating this also. This is a Japanese game show. Where people put a high molecular weight polymer solution, an aqueous high molecular weight polymer solution, onto this stair, and this leads to a surface that is almost or quite as slippery as ice. This is an effect that was well known. It's been used by the riot police in several countries. If there's a manifestation, they spray this on the ground and the manifestation is over. But how this works is still a puzzle, and that's what we're investigating right now. So thank you very much for your attention. And if there's any questions, I'm happy to answer them.
Okay, thanks very much, Daniel, for a very informative seminar. The seminar is now open for questions, so if you have a question, please raise the little hand, blue or yellow, whatever the case might be. Don't forget to unmute yourselves before asking your question. So do we see any little hands here? Who's got a question? Hello there. Oh, I see a little blue hand. Yeah, go ahead, Zemaria.
Well, thank you, Daniel, for this nice seminar. I have in fact, two questions. So when you have the temperature dependence of the friction coefficient at low temperatures, you have this energy. Do you have any, what is the origin of this energy? Or can you make an estimate of where it comes from? And the second question is about skating. So you are always assuming that you have to have a very low friction coefficient in order to skate, but I mean you need some friction to accelerate. So it cannot be that you must have here some kind of balance between low friction and enough friction to accelerate, isn't it? Or am I wrong?
Well, so the friction for acceleration, if you look at this skate, comes from the sides. So the sides are very sharp.
Okay. Mm-hmm.
And that's what allows you to have a high friction with the ice. But then while you glide, you have to have a low friction. Yeah. So the skate is made such. So if you would have a round bottom of your skate, you wouldn't be able to skate. You really have to have, and so the question about the activation energy,
yeah.
We know what the activation energy for surface diffusion should be, and we actually find something very similar as the one that was found by Kingery for this sphere sintering experiment. Mm-hmm. So it's just a few kT. Mm-hmm. Okay. We're trying to do better in the self-healing ice experiment, where we can quantify things much better than either Kingery or our skating experiment.
Mm-hmm. Mm-hmm. Okay, thank you.
Right, okay, so next question is from Carlos Monferro. Please ask your question.
Well, thank you for your presentation. I'm actually a student in computer science, but I was just wondering if the thickness of the ice when you touch is similar to this process, or is it related, or is it completely different? Thank you.
Sorry, the thickness of?
No, the thickness when it sticks.
Ah, the stickiness.
Is this related to what you have been explaining?
Yeah. So that's actually the picture that you see here. Yeah, so there are two ice spheres. And if you just keep them together, the neck between the two will grow. Yeah, and that's what you call stickiness, because they really sinter together. But the growth is not because of a water layer, but the growth is because of surface diffusion.
Okay, thank you.
Does that answer your question?
Yeah, I think so. It's the same process when you touch an ice cube with your finger, right? And it sticks to your finger just because you touch.
It might. I actually don't know. That's an interesting question.
Okay, because it seems like the opposite. So I was just wrong.
Yeah.
Thank you.
Right, so next question from André Matias.
So, hi. My question is regarding the plot that you have about the friction versus the temperature, and I'm not sure if I fully understood how you measure the friction. Can you explain how you measure the friction experimentally?
Yeah, sure. So let me go back. So this is the experiment. This is a sphere. And so the machine that makes the sphere turn is a rheometer, and that measures the torque necessary to rotate the axis, but it also measures the force that the ice exerts onto the ball and vice versa, which we call the normal force. And so the ratio between the two forces that simply comes out of the machine is what we call the friction coefficient. It's what everybody calls the friction coefficient.
Okay, but later on you comment that the friction the dependence of the friction the force versus the normal the friction versus the normal force, it's not linearly, so that the plot of the friction coefficient should depend on the normal force.
Yeah, so that this plot you mean?
Yes.
Yeah, so this gives a range of friction forces for the blue and the red curves. But what we do is we simply give an error bar from the slope at the beginning to the slope at the end. But the variations of friction force are much larger than the curvature of these lines.
Okay, so and my last question is, when you change the normal force, you don't expect the line of the friction coefficient versus the temperature should not change.
Right.
Even and I was wondering about the plowing, because if you increase the normal force, the plowing should be different or not.
Yeah, so the plowing force is the normal force to the power 3/2. So this again gives a friction coefficient that is not very well defined, but it gives a range of friction coefficients between the smallest and the largest normal force that we apply, if you like.
Okay, thank you.
Yeah, so
Right.
if we can no longer talk about the friction coefficient, the whole discussion becomes very, very complicated. Interesting, but complicated. So we represent everything as an effective friction coefficient, if you like.
Right, now a question from Margarida.
Oh, hello, Daniel.
Hey.
I'd like to ask you a question which is not, of course, it's not very relevant for ice skating, but if the mechanism is this mobility of the surface molecules, as you claim, this should happen in other solid materials, you know, at least some that have similar structure to ice. Is that at all known? I mean, not for ice skating, of course, but you can think of applications where you have other materials with the same type of structure, with surface mobile molecules, and therefore the friction or the friction coefficient should have the same type of behavior, right?
Yeah.
I mean, it's just structure and diffusion.
Yeah, so that's a lovely question. We are very actively thinking about that. The experiment we did was on lead, because we know from lead that there are some crystalline phases that show surface melting and others that do not. The problem with lead is that you always get plowing. It's actually too soft. So what we think is the specificity of ice is that it remains very, very hard, almost up to the melting temperature. Yeah, it's only very close to the melting temperature that you get this plowing, and that's why you can skate. And so our feeling, but we're trying to quantify that, is that for other materials, they already become soft way before the melting point. And then you always get plowing.
What about diamond? I'm pretty sure you could do it on diamond.
Yeah, I'm not sure. So I think the diamond in our plot is on such a low temperature, if you like, that you always will get a high friction coefficient. And what you would really want is to measure the Arrhenius behavior while going to melting. Right? I don't know how to melt a diamond.
No, neither do I. And then, yeah. Yeah.
But it's a very interesting question. That
you could do it on the computer. And I mean, just, I don't know, the Emirates don't have any water or snow, but maybe they can skate on ice or on diamond or something.
Yeah.
You show the polymer stuff, so maybe that's much cheaper. But it must, for the polymer, the mechanism has to be somewhat different. But you're thinking about it. So I don't see how the surface mobility would work.
So if you think about this surface mobile layer as supporting some of the normal force that you're trying to exert, the polymer by its elasticity does something similar. That's what we think that happens.
Okay, thank you. Very nice talk. Yes.
Thank you.
So all the water that the Egyptians put, I mean, that's a different problem, because then you have.
You'll have to invite me again.
I know. I've heard your talk on the sand. Anyway, some time ago in some conference or other. Yeah, we'll invite you again. Okay. Thank you very much.
Okay. One more question from Nuno.
Daniel, thank you very much for your talk. My question is related to the surface. So how do you prepare the high surface, and how much the results will depend on the way you prepare this surface?
So the major problem is humidity from the air condensing onto the ice. So basically we do everything in a dry box. Otherwise this would be completely white, all of it. We've tried different preparations of ice. We even tried, I should actually put up the references for those who are interested. We've even tried monocrystalline ice, and there's no difference. Yeah, so different ice preparations do not seem to give different friction coefficients. So that's in the JFIS-Chem letters, and so the FISRFX is just out, just a couple of weeks ago.
Okay, but when you keep using a surface for ice skating, you know that once in a while we need to stop in order to make it flight again. So is there any insight that we can get from here such that we could, for example, extend the time that we could ice skating without stopping for treating the surface?
Well, so the treatment of the surface again, so basically they melt the upper layer and it freezes again, is because of plowing. because you get all kinds of ice grains over your ice skating rink. And I don't think there's a real way of avoiding this.
Thank you very much.
Right. Any more questions? Do we have any more questions? I don't see any more raised hands. Anyone? No. Okay, so maybe it's time to wrap up. Okay, Daniel, thanks very much. Thanks to everybody for coming, and we'll be back next week with another seminar in our series. Oké, Daniel, hartelijk bedankt. Tot de volgende keer, hopelijk persoonlijk. En doe ook de groet aan Misha van mij.
Will do.
Oké, bye. Bye, everybody.
Okay, bye-bye. Thank you, Daniel.
Bye, Margarita.